Hi, this is Miss Alberg. Today we're learning how to draw free body diagrams. And free body diagrams, the name is a little bit weird, but we are going to learn how to take an object and we're going to free that object from its body and represent it as a point. And we're going to take that point and we're going to draw all the forces acting on that body in the direction they occur, and we're going to name them. We're going to name the type of force. And so let's get started. So step one is to kind of sketch a diagram. If you don't have a picture, sketch a little diagram. A tractor pulls a log at a constant speed. And so if we have a tractor, and here is my tractor, and it's pulling a log. Here's my log. And moving along, and it's going at a constant speed. I have my little diagram going on. Now, constant speed, we have something not speeding up, not slowing down, not turning. It's going at a constant speed. And so this is our code word for balance forces. So we know that when we draw our forces, we are going to have balanced forces. If it said speeding up, we would know we'd have unbalanced forces. So let's go ahead and get started. So after you have your picture, we're going to enclose the log within a closed boundary line. So let's go back to this picture. We are drawing a free body diagram on the log. So in order to make sure we're looking at the log and all the things acting on the log, we're going to draw a circle around the log so we can isolate the log in our system. So the next thing we're going to do is we're going to shrink the system to a point at the center of coordinate axes with one of the axes parallel to the direction of motion. So in other words, we're going to look at this log and we're going to say if it's moving, it's going to move horizontally. And so we're going to have an axis that's X and Y, horizontal and vertical, and we're going to take this log and it's going to be a point at the center of our axes. And so the next step is to identify the forces. And if we look at the forces on the log, we're going to look at all the things touching the log, and we're going to name it in a very special kind of way. We're going to name the kind of force on the feeler by the dealer. In other words, what type of force is it? Who's feeling that force? Who's causing that force? And so let's go back to our picture of our log and let's take a look at our log. And so if we look at our log, let's look at all the things touching the log. Now the thing that you see in this picture touching the log is a rope. The tractor's pulling it with a chain or a rope, and that kind of force has a name. It's called tension. So Ft is the name of that type of force, tension. And if we look on the next thing, type of force on the feeler by the dealer. Who feels this force? The log feels this force. So it's on the log by the, who's the thing causing that force? The rope. So if we name it on type of force on the feeler by the dealer, it's the force of tension on the log by the rope. Now, my picture is not the greatest picture because my log seems to be floating in the air, but there's actually like some ground there. And so the other thing touching the log is the ground. And so if we look at that, there's a force between anything that's touching the log. So if we look at that, there must be a force from the ground. Now, which way is the ground pushing on the log? It's pushing it up. And we always have a force anytime we have two surfaces in contact, and the name of that force is a normal force. And so this ground is going to push up on the log perpendicular to the two surfaces. So the name of the force on the feeler by the dealer, the log is the thing feeling the force, and the dealer is the ground. Okay, so right now we know we have balanced forces, but I only have two forces there, and if we look at those, this is very unbalanced. Balanced forces means that all the forces kind of cancel each other out, and so let's look at that. We have a normal force going up. Is there something pulling down on the log? And I'm going to put the arrow. We know there must be. There's not anything like physically touching the log, pulling it down, but instead it's one of those non-contact field forces. So gravity, the force of gravity, is pulling down on the log. And what is the thing that causes the force of gravity? The entire Earth is what causes the force of gravity on that log. And now, so these two are balanced, and we know we have to balance tension because we know that if it's moving at a constant speed, the forces have to be balanced. So there must be something going this way. So if we look at that situation, what is the only thing that could be acting on the log this way? And if we look at that, if the log is moving, this force is acting the opposite to the direction of motion, and it must be friction. So there's friction on the log by the ground. And so those are all the forces acting on our log. So now our next step is to represent all relative forces that cross the boundary with a labeled vector. We did that. And indicate which forces are equal to each other. And we're going to use congruency marks. So we're going to go back here. And we said all these forces are balanced. And since we only have one up force and one down force, we're going to say that they're the same size, because my arrows may or may not look like they're the same size. But if I put a congruency mark, now you know without a doubt that these two guys are equal to each other. Whatever this force of gravity is pulling it down, the normal force pushing it up is exactly the same value. And my sideways forces, or horizontal forces, tension and friction, also are the same size. And so if I put congruency marks like this, we might think that the friction is the same magnitude, like the force of gravity is 200 newtons, friction is also 200 newtons, so, and we don't know what it is, so we're going to add two congruency marks, because we know these two horizontal forces are congruent, or equal to each other, but we don't necessarily know that they're the same value as the vertical forces. And so this is how we do a free body diagram. So if you follow those steps, you will know all the forces acting on an object and the direction on which they occur, and then we can figure out maybe a few extra things later. So if we have a book at rest on a tabletop, so here's my table, and here is my book sitting on the table, and I'm going to circle it in red. First step, circle the object. So we drew it. We circled it. We circled it to identify the forces. So every place that the object is touched, there is a force. And so if we look at that, the book is only touching the table. So the table is putting a force on that book. And so we're going to start identifying those. So step one, draw it. Step two, draw your circle to isolate the object. Now we're going to shrink it into a dot. If it moved, it would move horizontal or vertically. And so we're going to draw our axes, vertical and horizontal. And now we're ready to draw and identify the things acting. So if the book if the book is pushed by the table, it's where those two are in contact with each other, and that is called a normal force. And so the table is pushing the book up. So there is a normal force on the book. A little trouble with my pen here. On the book by the table. Now, I know this thing is not moving. It's moving at a constant velocity of 0, and that is code for balance forces. So I know there's more than one force acting on that. So there must be a downward force. And what is that downward force? Yes, it's the force of gravity on the book by the Earth. Our last step, are these two forces equal? If they are, we need to put congruency marks, and we said if the velocity is 0 or a constant velocity, we have balanced forces. So yes, these two guys are equal. Okay. Now we have a girl suspended motionless from the ceiling by 2 ropes. So here we go. Here's our girl, and she is holding on to some ropes hanging from the ceiling. And so if we draw a circle around our object, we have our girl in the center. We're drawing the free body diagram on the girl. And so if she moved, she would probably fall down. So we're going to do a horizontal vertical axis and shrink her to the point in the middle of that axis. And we're going to draw all the forces acting on her. Now the things touching her are these 2 ropes. And so, and each of them pulls up at an angle. And actually kind of looks like in the picture at the same angle. So I tried to draw that there. And so if we label this, this would be the force from the rope. And that force from the rope is called tension. So we have, so tension on the girl by the rope. And because we have 2 ropes, I'm going to call this the force of tension 1, and this one will be the force of tension 2. And so that one is also on the girl by the rope. Now I know these forces are balanced because her constant velocity of 0 means that we have balanced forces. And so if we have 2 upward forces, part of this pulls to the right, part of this pulls to the left, so we can see where this would kind of cancel out. But we must have a vertical force, and that last force, we can't really see gravity's force field acting on her, but we know that she is subjected to the force of gravity. So we have the force of gravity on the girl by the Earth. Okay, and if we look at this, the last step that we didn't really talk about is if we have forces that are not on the axis, we're going to break these into components. So if we look at this force of tension 1, part of this force goes horizontal and part of it goes vertical. And we're going to label that FT1X and FT1Y. On this one, we have the same thing going on. We have part of this force is horizontal, part of it is vertical. So we have FT2X and FT2Y. 2y. Okay. Now in purple, actually let's do it in black. In black we're going to draw our congruency marks. We know that everything's balanced because her constant velocity is 0. And so if we look at this, the horizontal components of these two must be balanced because we only have two horizontal components and they're opposite each other. Now the other thing we know is that this downward force of gravity is balanced by these two upward forces from the rope. But we can't put congruency marks because this one equals the two of these combined. So no congruency marks on the up and down forces, but we could write an equation if we wanted. We could write that the force of gravity equals Ft one y. Okay, let's see. Let's erase that and start that over. Ft1y plus Ft2y. So in other words, and I'm going to circle those in black, these two right here, if you add them together, they will equal the downward force of gravity. So we can't put congruency marks on those guys, but if we needed to, we could write an equation. We could also write an equation for these two. We could say Ft2x equals Ft1x. And so if we wanted to write an equation for these two guys, we could. Our congruency marks also tell us that story. Okay, here is another one. So we have a little flying squirrel. So here's our little squirrel. And his arms are in. He just jumped from a tree to the ground. His wings are not flapping. He's moving at a constant velocity. So he's just gliding. It says, consider air resistance. Diagram the forces acting on the squirrel. And so if we did our first thing, we drew our little squirrel. Our second step is to isolate the system, draw a circle around it. If he would move, and he is moving, he's moving through the air, but we're going to use the up and down axis because, well, he's falling. We're going to draw the squirrel as a dot, and we're going to label the forces acting on the squirrel. Now, is anything touching the squirrel? So there are no objects touching the squirrel, but it does say consider air resistance, which means that there are little particles hitting the flaps of the wings as the squirrel is gliding down and pushing the squirrel up. So we have the force of air resistance. Sometimes this force is called drag. And it's on the squirrel. Ooh. Let's start that one over. On the squirrel by the air. Only other force acting on our squirrel is the downward force of gravity on that squirrel by the earth. Okay. So our last part, do we do congruency marks? Are these two guys equal? How do we know? Let's go back to our information, and it says at a constant velocity, which is code for balanced forces. And so if the forces are balanced, they do have congruency marks. Since there are only two, they must be balanced. So we know the air resistance up equals the force of gravity down. Okay, I'm going to skip this one and let's go to the car parked on a hill. So here we go. Let's sketch a car parked on a hill. So we have our car parked on a hill. We are going to isolate the system by drawing a circle around it. Now, if this car moved, it would move at an angle like this. And so to make our life easier, we are going to actually draw our axes tilted to the same angle as this hill. Now, if we look at this car, it's being touched by the ground. And so the ground actually pushes on this car with a normal force. Now, these two surfaces are in contact and the ground pushes the car perpendicular to the surfaces in contact. So there is a normal force, and that normal force on that car is actually at an angle because the surface is at an angle. And so this is a normal force on the car by the ground. Are there any more forces acting on the car? If we look at this car is on Earth, so gravity does pull on it. Now, which way does gravity pull down on you when you're on a hill? It pulls you straight down to the middle of the Earth. So straight down is always the direction of the force of gravity. And are there any other forces? Now, it says the car is parked on the hill, which is code for constant velocity is 0, which means our forces must be balanced. Do our forces look balanced? So our forces do not look balanced at all. There must be one thing we're missing. And in fact, if you look at this, what keeps a car parked on a hill from sliding down the hill? If you're not sure if friction is there, imagine it, what if it was missing? If friction were missing, this car would not be parked, it would be sliding down the hill. And so friction acts opposite the direction of motion. Now, if it moved, it would slide down the hill, so friction must act up the hill. So we have the force of friction on the car by the ground. Okay. Are these forces balanced? Yes, they are. How do we know? The car has a constant velocity. So in order to show that, we can't put congruency marks because we don't know that these are all equal, but we do know if we take this force of gravity and we break it into components, part of this force pulls the car down the hill, part of this force pulls on the car into the hill. And these two forces are at right angles to each other. This actual force of gravity is always the hypotenuse. And so this is FGX, and this is FGY. Now, if we look at that, we have two horizontal forces, and we can label our force of friction and our FGX as being balanced or congruent to each other by adding these two congruency marks. If we look at our normal force and our force of gravity, part of this force is actually into the hill. This force of gravity, and I'm going to put two congruency marks on this one, balances that normal force that pushes it out of the hill. And so we could say that our normal force is the same size as the vertical component of our force of gravity, and we could say our friction equals or is the same size as our horizontal component of gravity. So if we break the force of gravity into two components, then we can write these two equations. So enjoy. Go ahead and work on worksheet 1A. Bye.